And the next speaker, Igor Bychko from Pisarjevsky Institute of Physical Chemistry. And I'm happy to have chemist here. Please, Igor.
Thank you. So, can you see my presentation?
Yeah.
So, it will be a short presentation about, I think, our requirements as chemists who work with solid materials, and in particular with in the field of heterogeneous catalysis. Actually, in some part it will be continue from as previous speaker, Yaroslav Darchenko. However, I think I will represent some ideas from another point of view, and it will be useful. So, first of all, a few words about me and my organization. I'm a senior scientific researcher in the Institute of Physical Chemistry. It's placed in Kiev, near the Institute of Physics and near the Institute of Physics of Semiconductors. It's the oldest institute, chemical institute in Ukraine, and one of the oldest institutes at all. Actually, catalysis and heterogeneous catalysis is one of the main fields of our institute since its organization. Founding, and at present time we have 3 departments that works in the field of heterogeneous catalysis, one department as photocatalysis, and one department that works in the electrocatalysis. So in general, when we talk about catalysis, so it's a field that combines different parts. It's a typical chemical part is the synthesis of catalysts and providing catalytic experiments when we measure the dependence of the catalytic, of conversion or catalytic activity on the temperature. We investigate different chemical kinetics by variation of concentration dependence, and also we provide stability tests that are very important for industry, because in industry catalysts work in process about years, maybe 3 years. Of course it depends. Very important part, it's a characterization of the solids. And this is actually our weak place, because characterization requires really costly equipment. It requires a lot of different types of equipment that can provide absorption methods, spectroscopies, and electron microscopies, different electron microscopy, and also a set of methods that use X-ray radiation. I will say about this later. And also, we need theoretic investigations. We need specialists that can provide different DFT calculations, molecular dynamics, and can understand about band structure of solids, density of states, and some other. Generally, all catalysts can be separated on 2 types. It's an acid-base catalyst and catalyst for redox reactions. Acid-base, it's a typical alumina, cellulites, and resins, and some others, some such type of materials. While redox materials, it's typically metals, oxides of transition metals, maybe sulfides, maybe carbides. So this type. Here very important to mention that during chemical process, metals can be transformed into the oxides, and oxides may be transformed into the metals. And understanding what is the real state of active phase of catalyst is very important for creation and effective catalysts that is interested for industry. So reaction in this, in all cases, almost all cases, proceeds on the surface, and obtain, for example, method with very high surface is a very big problem. Actually, it's restricted due to a lot of reasons. And almost always metal-based catalysts are the catalysts with some type of support. It can be aluminum, it can be silicon, it can be, for example, activated carbon. And on this support, metals deposited in the form of nanoparticles. However, it's not only nanoparticles. The main idea, the smallest particles, the higher surface area. So, according to the reaction proceeds on the surface, we need surface area as large as we can create. So we need particles as small as we can create, but of course it's not so simple. So almost in all cases, catalysts are represents our atom dispersed metals on the support. It's so-called single atom catalysts. It can be clusters of metals that contain 2, 3, 10, 20 atoms of metals. It can be small nanoparticles. It can be bimetallic or 3-metallic nanoparticles. And also it can be nanoparticles of different morphology, different form, and different phase structure. So as I said, it can be particle with when part of particle is a metal, part of a particle is oxide, and another particle can be, for example, carbide. And proportion of these phases is depends on the reaction conditions. So we need to understand how it works. And of course, if we talk about catalysts, it is a solid material, but it is not a solid. It's not ultimately stable solid. And reaction conditions, chemical reactions are influenced on this solid. And this leads, for example, to the sintering of catalysts. So we can create, for example, catalysts with very small nanoparticles, but during reaction, these particles are sintering with creation of large nanoparticles. It can be also poisoned by some components of the reaction mixture. It can be, for example, be covered by carbon and therefore deactivated. So to understand what is the catalyst and how it works during reaction, we need to use different methods. And here I present methods that use X-ray radiation, and these methods are also in a lot of cases presented in synchrotron facilities. The main method is very useful and very powerful. It's X-ray power diffraction, but the main disadvantage of this method is that it does not allow us to analyze materials with with small nanoparticles. For example, if we have a phase with nanoparticles in the size of 2 nanometers and about this, X-ray diffraction just useful. We cannot see these particles. It's methods that use X-ray spectroscopy. I will say about this later a few words. It's also different methods such as X-ray emission spectroscopy. It's small angle X-ray scattering that is very useful, for example, for analysis of porous structure of materials. And near ambient pressure X-ray photoelectron spectroscopy, very useful method. However, the main disadvantage is that X-ray photoelectron spectroscopy XPS requires a high vacuum. So we cannot investigate our materials and our chemical processes in the conditions where these processes are provides in reality. So in XPS we need pressure about 0.1 millibars, whereas in heterogeneous catalysis typical pressures are from 1 atmosphere to 50. It can be even more. It can be even 100 atmospheres and so on. In our institute, we have very small experience in the work with equipment that have an X-ray tubes. It's only two units. It's a diffractometer and XRF spectrometer. So, and it is really our huge problem, unfortunately. So here I want to show in more details what I mean about XRD. So X-ray diffraction allows us to investigate the phase structure of solid materials in different conditions, in different temperatures, up to, in some cases I saw it up to 1000 degrees C, using special equipment, using special equipment. So in these cases, we can see as well as evolution of materials during its preparation, and also it allows us to provide research about the evolution materials during the catalytic experiment. But as I mentioned above, I draw your attention on this, that if the active phase, and active phase it's typically metal, is size of this metal, particles of this metal is less than about 3 nanometers, we just cannot fix any phase, and XRD in these cases are unfortunately useless for us. So the one option that we have to study materials with very small nanoparticles is an X-ray adsorption spectroscopies. It's XAF-XANX. As example presented on the slides results, and here I draw your attention that these experiments, these techniques allows us to understand the distance between atoms. That is very important to understand the configuration of metal clusters, And for example, for bimetallic nanoparticles, if we use not only one metal but different metals, it also allows us to understand what is the coordination state, what is valence state of atoms or particles in the materials during the catalytic experiment. And here I draw your attention on the conditions. So this spectra was recorded during such conditions where temperature of the sample was about 250 degrees C, and pressure in the reaction cell was about 30 bars. So it is as I analyzed for today, such experiments and such loadout is typical for a lot of synchrotron facilities. And for example, if we talk about Solaris, as I mentioned, the beamline Astra can provide such type of experiments. I also want to show you about how it works in practice, as I found in literature. Unfortunately I didn't saw by myself, but I can only represents how it works in principle. So it's some reaction cell where catalyst is fixed in the center, and this reaction cell first of all is heated, and this reaction cell is and this sample is in the flow of different different gases or vapors, combination of the temperature, gas mixture, and pressure, we can provide such type of experiments. And in typical case, of course, this cell also is equipped with gas analyzers of different type for providing an understanding. So how for example, selectivity of catalysts is combined with with its state. So, for example, in more reducive atmosphere where we have more hydrogen, it can be more metal in catalysts. But when we have a more oxidizer, for example, it can be CO2, we can have a more oxide phase. However, this combination phase are influences on the reaction products. And the reaction products we need to analyze using different gas analyzing techniques. So this was the main idea that I wanted to represent. And thank you for your attention.
Thank you very much, Igor. So as far as I understand, you do not have much experience with synchrotron, right? But it's interesting.
Unfortunately, no.
Because I wanted to ask, like Yaroslav shown about escape depths, what do you think optimal? But I think it will be, we can discuss it later when you have experience already. But we should discuss actually the requirements for this beamline at Solaris. So it is important, but this is of course not in form of questions. Yaroslav, please.
Yeah, I just want to say, yeah, Igor, thank you so much for this excellent talk. I must say that it's probably your talk should be before mine, because you so nicely explained, about catalyst, what it is about, how they work, and also like in terms of techniques, I guess there is better overview, and I just pick up a small thing out of it. But yeah, thank you. And then I just wanted to say that essentially also that there is like say an opportunity to collaborate, I guess, with with people from Synchrotron is just trying to build some cells there as well, so they could sometimes have a need, or they don't have specific. So I guess yeah, what I would say, if you try to write a proposal, obviously if you want to do something more complex, like some reaction, maybe doing like in situ. Actually, we call it operanda, because you have like not only like in situ is typically when you do some heating and just see some transitions, but actually here you are actually doing the operanda means that something is kind of working. Yeah, there's material which is obviously functional, and something is happening, and then you're just looking how structure is evolving, how chemistry is evolving, and it's an excellent opportunity for your work, what you showed. I mean, to find some collaborators. And I mean, the good thing that obviously what you want to do, you can approach people at the beamline, and after if you build something, it would be like a shared setup, shared cell, and then other users can use it as well. So it's like win-win situation here for them and for you as well. So you could you can, and also it could be like a long-term proposal. What we have done in the past at ESRF, there was like I don't know whether they exist now. I mean, I guess some of the attendees now can comment. It's what's called like LTP. It's a long-term proposal. So you write a bit more, you spend more time, but instead of getting like only one beam time, yeah, which is like 3 days, 1 week, you get whole you get like time for the 3 years. Yeah, you have lots of like for a granted time, and you can plan your activity, because obviously commissioning a cell, it's much more complex. Yeah, you cannot just do something, yeah, come there, stick it there, and it will work. Yeah, assuming it will work. Obviously, it will require multiple visits. It can be long time collaboration. Just saying that, yeah, good luck with your work, and I hope to see you.
Thank you, Yaroslav. I think we just need to maybe talk separately. I think I will say to you, it's very interesting. Maybe we will find some opportunity for collaboration. Thank you.
Surely, yeah, Igor. Yeah, we stay in touch. Yeah, surely, yeah. Just feel free to contact as well. Yeah, I would be happy.
Thank you, Yaroslav. Thank you, Igor. It's clear problem for me, an understandable problem for me. Or what you say. For us, it would be interesting also, for example, applying current to the sample and to see how it changes some composition. I think it's also similar thing. But okay, some more questions? No. Then thank you, Igor, and we switch to